Greetings to all. This is Sesha Vidya, working as Associate Professor in the Department of ACE at R.M.K College of Engineering and Technology. In this session, we are going to discuss Unit 1, Introduction to Optical Fibers. So under that, the subtopic topic is Propagation of Light in Single Mode Fibers. Let us start with the session. First, let me give the overview for single mode fibers. So as the name implies, it has only one mode of operation. In that mode, it is also called as linearly polarized mode, that is LP01 mode. And the single mode fiber which will have the core diameter of 8 to 12 micrometer, and core diameter must be just below the cutoff of the first higher order mode. And one more parameter called relative refractive index difference, and that varies between 0.2 to 1%. And range of cutoff wavelength recommended for the single mode fiber, and to avoid the modal noise as well as dispersion problem is from 1.1 to 1.28 micrometer, particularly and practically we'll be using 1.3 micrometer. In the next parameter called normalized frequency, in which will give that ability of the fiber, or we can say that the light gathering capacity of the fiber. So this normalized frequency for the single mode fiber, it should be in the range of 0 to 2.405. In this normalized frequency and for the single mode fiber, that can be adjusted within the range only by reducing the core radius as well as refractive index difference less than that of 1%. So this is about the overview of mode fibers. Let us consider the formulas that can be used for the single mode fibers. Normalized frequency, as I told you, it is a light gathering capacity, which is also called as V number. It ranges from 0 to 2.405. And second parameter that can be calculated for single mode fiber is cutoff wavelength. In the, as I told you, the range of cutoff wavelength should be from 1100 nanometer to 1280 nanometer. In terms of micrometer, we can call it as 1.1 to 1.28 micrometer. And this is the formula that can be used to find out the cutoff wavelength for the single mode fibers. And in this, this A represent core radius, N1 is nothing but refractive index value of the core, and del is nothing but relative refractive index difference. So by substituting all these values, we can able to find out the cutoff wavelength. And this cutoff wavelength lambda c, and it should be that's a it should, for the particularly for the single mode fiber, and it should be within that range. And by comparing that cutoff wavelength lambda c with the normal wavelength lambda, we can able to find out the relationship between this lambda c and lambda, which is nothing but lambda c by lambda, which is also is equal to v by vc, where vc is nothing but cutoff normalized frequency. And this cutoff value of normalized frequency Vc for the single mode of operation, and for the particularly for the step index as well as for the graded index fiber, is given by, and this is normalized frequency for a single mode step index fiber Vc is equal to 2.405. Similarly, for the graded index fiber, it should be 2.405 of 1 plus 2 by alpha whole power 1 by 2, where this alpha represents its refractive index profile number. So as we that's discussed in the last session, and for the graded index fiber, we know that the refractive index profile shape is a parabolic, so that the alpha is equal to 2. So by substituting this alpha is equal to 2, we can able to find out what is the cutoff normalized frequency for graded index fiber. And next one is nothing but mode field diameter, which is also related to the single mode fibers. And this is a single mode fiber will be considering. This is a N core, this is a N clad, refractive index value of the core and refractive index value of the cladding. And while this light is propagating within that core, that is within the single mode fiber, so we'll be getting that the electric field distribution, and this can be represented like this. So here it is mode field diameter is nothing but 2 omega naught, and half of this mode field diameter we can call it as spot size. So this mode field diameter will which will characterizes the functional properties of single mode fiber. And this omega naught, as I told you, it is also called as spot size. So spot size that can be calculated from the mode field diameter divided by 2, so that it is omega naught. And this gives the E of R is nothing field distribution. And this mode field diameter, and it can be determined from this mode field distribution of the fundamental mode of operation. And this is used to predict fiber splice loss, bending loss, as well as cutoff wavelength. And we can also calculate the waveguide dispersion also. And first of all, to find out this mode field diameter, we required two conditions. One is First, we have to measure the far field intensity distribution, that is E2 of R, and then we should calculate the mode field diameter by using that formula Peterman 2 equations. And this is a formula that can be used for the mode field diameter, which is important parameter related to the single mode fiber. Only by means of this single, that is a mode field diameter, we can able to predict the types of losses present in the single mode of operation. Next comes propagation modes in single mode fibers. In any single mode fiber, it has two propagation modes, which are also called as regenerative modes. And we can call it as one is horizontal, the other one is vertical polarization. These two modes propagate with different phase velocities, and this difference between their relative refractive indexes is called the fiber birefringence. So beta f is equal to ny minus nx. So definitely, well, this that's two modes of propagating, which will just propagate with different velocities. Due to that, there will be variations in the relative refractive indexes of the core and cladding. That difference, it is also called as fiber birefringence. And this is also called as free space propagation constant. B is equal to K naught of Ny minus Nx. So this K naught is nothing but 2 pi by lambda, which is also called as free space propagation constant. So as the conclusion, we can say that, so because of this asymmetrics, the refractive indexes for the two degenerative modes will be different. This difference is called as birefringence, that is fiber birefringence. So this is our next one is one polarization mode will be delayed in phase related to the other as they propagate in the single mode fiber. So as I told you, when this difference is a multiple of 2 pi, then these two modes will bend each other, that is will beat each other, and the input polarization state will be reproduced. So the length over which the bending occurs is called as fiber beat length. This is another parameter that can be found in the single mode fiber when there will be two phase differences between two modes of propagation, that is a integral multiple of 2 pi. So the length over which the beating occurs is called as fiber beat length. So as I told you, this is a two degenerative fundamental modes in fibers. One is horizontal, the other one is vertical, and we can call it as HE11, where H is nothing but hybrid mode and 11 represents L and M. And this is also one of the formula to find out the beat length. Next one is linearly polarized modes. So fibers are constructed so that N1 minus N2 is less than that of 1, where N1 is nothing but core refractive index and N2 is nothing but a refractive index value of the cladding. When the difference between this N1 and N2 is very very less when compared to 1, then that's the fibers which will generate the linearly polarized modes. The field components are called as linearly polarized modes and are labeled as LPJM, where a J and M designates mode solution. Now we can just able to see that what is that the correspondence between the lower order in the linearly polarized modes and the traditional exact modes from which they are formed. So LP01, which is formed from HE11 mode. LP11, which is formed from HE21, TE01, TM01. So already we know what is T waves, TM waves and HE waves. So this T waves is nothing, T waves are nothing but transverse electric wave. TM is nothing but transverse magnetic wave. HE is nothing but hybrid modes. So likewise we can able to differentiate the difference between linearly polarized modes and exact modes. So this is a pictorial representation for a linearly polarized modes with hybrid modes. In this third column which represents field distribution, the last column which represents intensity distribution of EZ. And one more thing is we will be considering that light is propagating only in Z direction. So the last column which gives the intensity distribution, we can able to see in that laboratory also, and for the single mode as well as for the multimode. And next comes a leaky and guided mode. So we are going to see what's the difference between leaky and guided modes. So first one is the limit of mode propagation, that is N2K should be less than that of N1K. So that is beta should be within that range. So only when this condition satisfies, only that is modes which are propagating within that fiber, we can call it as guided mode. If there is any deviation in this condition, then we can call it as leaky modes. So for example, the one more thing is cutoff. When beta is N2K, the mode's phase velocity is equal to the velocity of light in the cladding. And this mode is no longer properly guided, so that which will be cut off. So that mode is said to be cutoff mode. Next one is unguided modes. These unguided modes are also called as radiation modes or leaky modes. So for which the frequencies are below the cutoff. So that is beta is less than that of N2K. So modes exist near the core cladding interface. So solutions of wave equation giving these states are called as leaky modes and often behaves as in very lossy guided modes rather than the radiation modes. So next comes guided modes. As I told you, for beta is greater than that of N2K, less power is propagated in the cladding until beta is equal to N1K. So all the power is confined to the fiber core. So that we can call it as guided mode. So the conclusion is that, and for the guided mode, that is the light ray that has to be propagated through the core, the condition is that N2K should be less than that of beta and N1K should be greater than that of beta. So only this condition satisfied, there is an guided modes that will be propagated in the fiber. So this is overview of modes. A mode remains guided as I told you as long as beta satisfies the condition that N2K should be less than that of B and N1K should be greater than that of B. And where N1 and N2 are the refractive indexes of core and cladding respectively. And as already we discussed, K is equal to 2 pi by lambda and this is a free space propagation constant. And the boundary between the truly guided modes and the leaky modes is called as the cutoff condition, that is beta is equal to N2K. So as soon as this beta is less than N2K, the power leaks out of the core and into the cladding region. That's nothing but leak. And the order of mode is equal to the number of field zeros across the K. The order of the mode is related to the angle that the ray concurrence corresponding to this mode that makes the plane of waveguide. That is steeper the angle, then higher the order of the mode. And leaky modes are only partially confined to the core region and attenuate by continuously radiating their power out of the core as they propagate along the fiber. This power radiation out of the waveguide results from a tunnel effect. So this is a way of modes. And next comes under summary. So the exact solution of Maxwell's equation for a cylindrical dielectric waveguide, that is very complicated and which gives the complex results. Cylindrical waveguide is bounded in two dimensions, therefore two integers that can be used. One is L, the other one is M. So that both L and M which will specify the modes. So TLM, TM, LM modes. So this modes results from meridional rays propagation, that is propagation is within the gate. In optical fibers, the coupling between E and H fields results in HE or EH hybrid modes. So the hybrid modes where both EZ and HZ are non-zero and which results from skew ray propagation within the fiber. The two lowest order modes HE11 and T01, the subscript refers to the possible propagation of modes in the optical field. And fibers are constructed so that N1 minus N2 is less than that of 1. So the field components are called linearly polarized modes and are labeled as LPJM, where JM and M are designate mode solutions. Thank you for your patient listening. Thank you one and all.